Hi friends, let's understand the limitations of basic RAG and why we need adaptive RAG with self-reflection. Okay, so here we have the basic RAG architecture. First, we take the documents, we chunk them into smaller pieces, create embeddings and index the embeddings / documents in a vector database. And then the user asks the question, we use a retriever to retrieve the top n documents. We provide to the LLM those documents as context along with the question and LLM generate the response. That's the basic RAG system. Now let's see what are the limitations involved in this. Okay, so the first one is the user might have asked a very basic question or very general question, or it could be completely unrelated to what we have in the vector store, right? But even then, we still go ahead and use the retriever to retrieve the documents. Okay, so the first limitation the RAG system have is it doesn't know if it should retrieve from the retriever or if it should go ahead and answer because it is a too generic question, or it should go and maybe search the web, right? So the first one is the routing problem. And let's say it's went ahead and it retrieved some documents. Now we are passing the retrieved documents along with the question straight away to the LLM. So we are not checking if the retrieved documents are actually relevant to the question. Okay, so we are not grading the retrieved documents. That's limitation number 2. Okay, now let's say the documents are indeed relevant. Okay, that's fine. So we pass them to the LLM. Now here we have the answer generated. We need to check two things. One, is the answer generated actually grounded in the retrieved documents, right? Or the context. Because the reason why we are providing context to the LLM is so that the LLM generate the answer based on the provided context, right? Sometimes these LLMs, they hallucinate, right? So we are not checking if the generated answer is grounded in the provided context or is it hallucinating. So that's the third limitation. And finally, the fourth limitation is whatever the answer generated, we pass it back to the user, right? We are not checking if the generated answer actually addresses the question by the user. Okay, so that's the fourth limitation. To quickly summarize, we have 1 routing issue, 3 grading issues. The routing issue is irrespective of what the user question is, we straight away go to the vector store to retrieve the documents. Even if the question is very generic, it could be answered without a vector store, or it is completely unrelated to the vector store. And then the 3 grading issues are, we are not grading if the retrieved documents are actually relevant to the question. And then once the answer is generated, we are not grading if the generated answer is actually based on the retrieved context or if it is an hallucination. And the fourth or the third grading issue is we are not grading if the generated answer actually addresses the user question. Okay, so these are the 4 main limitations of the current or the basic RAG systems. Now let's see how we can address all these 4 issues in adaptive RAG with self-reflection. Okay, so this is how it looks like. When the user asks a question, instead of straight away going to the vector store, here we have a query analysis or a router. So what it does is it will check if the user asked question is actually relevant to the index or the vector store we have built. Only if it is relevant, it will go ahead this path. Otherwise, it will take different routes. Now, if it is not related to the index, we might give it web search capabilities. So it go ahead and search the web. From there, it retrieve the context and then generate the answer. Or we could have a third route, which is this query analysis figure out. This is a too basic question. It neither need a vector store nor need a web search. The LLM already knew the answer. Okay, so it can straight away answer. Or in a complex scenario, we might build a very big RAG system where we have one store or one vector store for medical documents, another for finance, another for HR, etc. Right? So the query analysis figure out what sort of question it is, and it will route to the appropriate vector index. Okay, so that's what the query analysis does. So we have addressed the routing issue here. Okay, and then let's say the question is actually relevant to the index we have built, and we have retrieved some n number of documents for context, right? So the second one is we are not grading how relevant the retrieved context is to the question, right? So what we have here is a grading node. So this grading node, it go through all the retrieved documents and it will grade all of them against the user query. Okay, if let's say we have retrieved 5 documents and only 3 of them are relevant, so what it does is it ignore the 2 documents which are not relevant. It pass only those 3 documents which are relevant to the generation node. Now let's say all 5 are irrelevant. So what it does is it says, hey, all these questions retrieved documents are not relevant. Maybe I'll reframe the question so that when I do the retrieval again, I will get better results. Okay, so depending on the quality of the retrieved documents, either we go ahead and generate the answer, or we rewrite the question to retrieve the relevant documents in the next step. Okay, so we have addressed the second limitation, okay, which is here. And let's say the documents are relevant, we provide them to the LLM and it came up with an answer. And then we had 2 limitations, right? Is the answer actually based on the provided context? Is the answer addressing the user question? Okay, so 2 more limitations we have to address. All right, so here we have the answer is generated, and then here we have another grader which check if the answer is a hallucination or if it's grounded in the provided context. So if it is a hallucination, it asks the generator LLM to regenerate the answer. Okay. Now let's say the answer is actually grounded in the provided context. Okay, then here we are addressing the final limitation. Okay, here we have an answer now, but is the answer actually answering the user query? If it is answering, then we provide the answer back to the user. Okay, if it is not, what we do is we go back to this question rewriter. We ask it to rewrite the question so that the retriever can retrieve the more appropriate or more relevant documents as context. Okay, so that's how we are addressing the 4 limitations we have in the traditional RAG system. Okay, the reason why it is called self-reflection, because after every step it is reflecting if the output make sense or not. Okay, so we have three grader. The retriever grader, the answer groundedness grader, the answer correctness grader. Okay, so these three reflections we have, and we also have a router at the very beginning to decide which index should we go to if there are multiple indexes, or if we should go to an index at all. Okay, so that's the adaptive RAG system with self-reflection. All right, now let's see how to implement this using LangGraph, which is a new capability from LangChain. All right, some standard libraries. Okay, so I'm going to use OpenAI, but you can use any open source LLM as well. We don't need this Cohere, but in this example, if the question is not relevant to the index, we are going to do web search. So for that web search, we need this Tavily API key. Both OpenAI and Tavily I have in my environmental variable, so I don't need to set it here. All right, and you don't need this LangChain tracing or Langsmith keys. That's for tracing. All right. Okay, let's go ahead. The standard RAG, I'll go a bit faster because otherwise the video becomes too long, and I have covered RAG in multiple previous videos. All right, so first we need some documents, right? So here we have some blog posts on AI agents, the prompt engineering, some advanced attacks, etc. Okay, so these three are going to serve as our knowledge repository. All right, so we need an embedding model. So here we have the embedding model. All right, so using this web loader, we are reading these three blog posts. We got all the documents, and then using recursive character splitter, we split the content of these three documents into smaller pieces of size 500 tokens. Okay, so here we have the splitted documents, and then we are using ChromaDB. We give it a name, we provide all the splitted documents. So these could be a few thousand documents, right? Or few thousand vectors. All right. So then we have created a retriever. All right. So we built this part. So we have built this knowledge repository or knowledge base, specific knowledge base. Now let's build. So what we are going to do is, first we are going to build all these components. Okay, that's step number 1. And in step number 2, we convert these components into graph elements. And in final step, we put all these graph elements together to make this graph network using LangGraph framework. Okay, so first let's build all these individual components like router, the retriever node, the grader, the hallucination grader, groundedness grader. Sorry, these two are the same. Then the answer relevancy grader. Okay, so all these we will build. We will also build this web search tool using the Tavily framework. Okay, or API. All right. First, let's build this router. Okay. So the router job is to simply first analyze the question and figure out if it is relevant to the index we built. Okay. All right. Now, all the nodes or the capabilities we are going to build, they follow similar a pattern. So let's spend some time on this and we can go over the rest a little faster. All right. Okay, so this Pydantic library, it's a very nice and useful library for enforcing the particular data type when we write different functions, what type of input it should take, what type of output it should take. So it automatically do the checks for us. I mean, it does more than that, but that's the basic usage. Okay, so here we define a class route query. Okay, so what it does, it route to the most relevant data sources. As we discussed, these data sources can be the vector store, the web search, maybe a different vector store, or it could be directly sending straight away to an LLM. Okay, so in this case, we are going to have only two, which is a vector store and web search. Okay, here we provide some description. Hey, given a user question, choose to route it to web search or vector store. Okay, we have not provided the prompt yet how it should actually do the job. We simply said what should be its output. Its output should be either a vector store or a web search. Okay, that's all we define in this Pydantic base class. All right, then obviously we need an LLM at every step, even for router, for grader, for generating the answer, for everything we need an LLM because it is the brain, right? So everywhere we have this text in this system, and we are going to use LLM to understand the text to decide the next steps. Okay, all right. So here we have the actual system prompt. Okay, you are an expert at routing a user question to a vector store or web search. Okay, all right. The vector store contains the documents related to agents, prompt engineering, and adversarial attacks. Okay, so this is the most important part. We should clearly define what our vector store should contain. Then only the router can decide if it should route it to the vector store or not. Okay, so this part is very important. And then use the vector store for questions on these topics, otherwise web search. Okay, because we have only two options here. Okay, so here we have the route prompt, which is this the system message or this persona, how it should behave like, and then we supply it with the human question. Okay, so it takes the human question, it takes this prompt to decide whether to go for vector store or to the web search. Okay, now here we are just chaining different components together, the question router, so the router prompt, and then this structured LLM router. Yeah, all right. And then let's ask a question which is relevant to vector store and not relevant to vector store and see if it is doing the proper job. Okay, so the first question we are asking is, who will bears the draft first in NFL draft? Okay, obviously this question is completely irrelevant to what we have in the vector store, which is about agents, prompt engineering, and these adversarial attacks, right? So the answer to this question should be web search. Okay, so which is what we have. So the router is saying, hey, you should do web search instead of going to the vector store. Okay, which is good. And the second question, let's say we ask a question which is relevant to it. Okay, what are the types of agent memory? Since our vector story about agents, which must or probably have an answer, what the types of agent memory, it's a relevant question. So it says, hey, go to the vector store. Okay, this is good. We have built one component, which is this query analyzer / router, okay, which takes the user question to figure out if we should go to the vector store or we should go for web search. Okay, we built one component. All right, now let's grade the documents, right? We have three graders: grading the documents, grading if the generated answer is grounded or hallucinated, and the third grader is if the generated answer is actually addressing the user query. Okay, all right. So as I mentioned, the component, it's very similar pattern to this one. So again, we have a base model. Now the output is yes or no. So if the retrieved document is relevant to the question, it says yes, otherwise no. Since we are going to retrieve multiple documents, so for each document, it will say yes or no. Okay. Again, we have an LLM as a brain, and this one is the important part. Okay. So we say you are a grader assessing relevance of a retrieved document to a user question. Okay. If the document contains keywords or semantic meaning related to the user question, grade it as relevant. But here we don't want to be too strict because some of the documents, maybe let's imagine we have a retrieved document with 10 lines, right? Maybe the first 2 lines are important in addressing the question. The remaining 8 may not be that relevant, but still the retrieved context is useful, right? So that's why here we are saying it does not need to be a stringent test. Okay, the goal is to filter out erroneous retrieves. Okay, even if the relevancy is small, we still mark them as yes. Okay, we just want to filter out the completely erroneous ones. Okay, this is important. Now give a binary score of yes and no to indicate whether the document retrieved is relevant to the question or not. Okay, all right. So the grade prompt, and again we change these 2 capabilities. So here we have a question simply saying agent memory. That's all the question is. Okay, all right. So we retrieve. I think by default we are retrieving 5 documents because we haven't decided how many documents we are retrieving. So when we build the retriever, by default it's I think it's 5. All right. So it retrieved 5 documents. Now here we take the very first document. Okay, this is the content of the first document, and we are invoking the retriever grader. Okay, so we need to provide a question as well as the document. So it came up with saying, hey, the retrieved documents is not relevant to agent memory. Okay, which is good. All right. So we know our vector store has information about agents, but we don't know if it also has information about agent memory. Okay, so that's why probably the document which is extracted, even though it is relevant to agents, but it does not have anything to do with agent memory, so it is graded as no. Okay, all right. And then so this one is just generating the answer. So we need to provide, let's say the documents are relevant, so we need to generate the answer, right? So this is a standard prompt. I mean, so like how we are writing all these prompts, the LangChain hub, they have some pre-built prompts which we can make use of. So this prompt, it's like, hey, you are an assistant, helpful assistant which addresses the user queries. Take the provided context and try to answer the user query based on the context. Okay, all right. Now let's build this hallucination grader. Okay, so once the answer is generated, we will check if the generated answer is actually based on the context we are providing. Okay, so exactly the same similar structure. So here we have a class. Again, the output is yes and no. Basically, its job is to check if the answer is grounded in facts. Facts meaning the context, the provided context. Okay, all right. Again, the brain, the important part is this. So here we are saying you are a grader assessing whether an LLM generation, which is the answer, is grounded in or supported by a set of retrieved facts or provided context. Okay, give a binary score of yes and no. Yes means that the answer is grounded or supported by the facts. All right. Okay, so it takes 2 parameters. One, the retrieved documents and the answer. So here we are providing the set of facts. So these will be the top end documents, and here is the provided answer. Okay, all right. Again we put together. So here we have the documents, here we have the generation. Okay, so previously we had a question which is simply the agent memory, and we had the retrieved documents, and the grader already said it is not relevant, but we are still going ahead and providing these documents to see how the output look like. Okay, all right. Now remember, here we are not grading if the provided generated answer is actually answering the user question. We are only checking if the generated answer is actually based on the provided context. So that is why we got yes here. Okay, it might confuse you. One might think, but this output should have been no. The reason it is yes is, even though the extracted context is not relevant to the question, but here we are only asking, hey, the answer generated by the LLM, is it actually based on the retrieved context or not? Okay, we are not asking if it is actually relevant to the question. Okay, so that's why the answer is yes. Okay, and let's build the final grader, which is this answer grader. Okay, again, this will also provide a binary output yes or no. The same stuff here, the system prompt, which is the important one. Hey, you are a grader assessing whether an answer addresses or resolve a user question or not. Okay, give a binary score, yes or no. Yes means that the answer provided resolve the user query. Okay, the same thing. And here we are asking, okay, the question and the generation. This is strange. This should have been no. I'll recheck. All right. So the question we are asking is agent memory. I see. Okay, I'll tell you why. So here when we check the grader, we have checked only the second document. So this document, there are top n documents, right? Document 0, 1, 2, 3, 4, and 4. So here probably there is only one document within this vector store which is actually relevant to the agent memory, right? So that document is retrieved as document 0, and then here we have the first document. This one is not relevant to the user query. So the grader said, no, this is not relevant to the question. But then when we check the answer to the generator, we have provided all the documents, not just one documents, right? So earlier we have checked only if the second document is relevant to the question or not. Whereas here we have provided all top n documents. Okay, so since the first document has the answer to the question, the answer grader said yes, the generated answer is addressing the user query. Okay, all right, and let's build the final component, which is actually not the final component. We have a couple of more components, but let's build this question rewriter. Okay, so here we saw sometimes even when the documents retrieved are correct, because of the hallucination, the generated answer is incorrect. So we know the index has the right documents, but in iteration 1 we weren't able to generate the correct answer. One way we could address this is maybe we rewrite the question LLM friendly / vector index friendly, so that it retrieve the relevant documents. Okay, so here we have this rewrite question component. Okay, so let's see that. Okay, so the question rewriter. All right, again we have a brain, and then you are a question rewriter that converts an input question to a better version. Okay, see, this is the important one. To a better version that is optimized for vector store retrieval. Okay, look at the input and try to reason about the underlying semantics, intent, or the meaning of the user. Okay, all right. So again, just the prompt thing, and here we have the initial question, and it should give us the formulated or the improved question. Okay, so earlier our question is simply agent memory, right? So we are supplying agent memory as a question. So this question rewriter, it came up with what is the role of agent memory, what is the role of memory in agent functioning. So this is much better version of the question as compared to simply saying agent memory, right? So using this question, now we can retrieve better documents from the vector store. Okay, all right. And if the router decided that the question is not relevant to the index, we wanted to do web search. So let's build a tool called web search tool. It's super easy. So we are using this Tavily search results. We want to have the top 3 hits. Okay, so that's the web search tool. All right. So we have built all the components. We have built the router, we have built the web search, we have built these 3 graders, the retriever grader, the generator grader for hallucination, as well as for the correctness of the answer. And the remaining components are part of the basic RAG system, which we have built them, right? So in the next video, we will convert the relevant components into graph components, okay? And then we put them together to make it a graph network using Lang graph framework, so that it's somewhat similar to a DAG framework. Okay, that's all for this video. Thank you very much.